Our next speaker is the world's leading expert in ionospheric electrodynamics. Atmospheric models AMI, time GCM, Wacom X, pulling everything together from the sun to the earth. He is a wonderful and patient mentor and an incredible volleyball player. Dr. Art Richmond.
Okay, thanks. I'm just going to give a very brief background of upper atmosphere research and how it developed at HAO, and I'm actually going to go back historically and first give a very brief overview of how our interest in the upper atmosphere developed. Of course, the earliest known phenomenon related to the upper atmosphere was the aurora borealis, and in this case, the aurora australis. There were a number of ideas, mystical and scientific, about what the cause of this might be. It took understanding, an important link in the understanding of this phenomena was recognition that the Earth has a magnetic field that has a strong influence on the upper atmosphere. Back in, it was 1716 that Edmund Halley observed an aurora and proposed that it was caused by magnetic particles streaming into the upper atmosphere along the Earth's magnetic field lines. This was actually not too far from what is really the case. Well, something we can do, it turns out to be fairly easy nowadays to go to Google Books and find old manuscripts that are searchable. I did this with a few of them, and it reminds me of in the 1970s when Jack Eddy explained what he had to do to research the Maunder minimum, and he had to go physically to a library and pour through books manually. Anyway, one of the early treatises on the aurora was by Jean-Jacques Dautrou de Mérin, who, quite interestingly, believed that the aurora was connected with the atmosphere of the sun. In fact, he believed that the Earth was embedded in the solar atmosphere. And, however, somewhat confusingly, he based these ideas to a large extent on the fact that zodiacal light seemed to have an occurrence somewhat related with the frequency of aurora. Probably these two are not really very much related. It was based on very sparse data at the time. Another thread of research that feeds into the upper atmosphere was research on electricity, just electricity in general. And it was discovered in the 17th century how to generate static electricity, and various researchers built machines, like there's one here, to charge up, produce static electricity, and see what happens when you connect it to various things. This was in the days before there was a requirement on proposals about the involvement of human subjects in research. And so one of the favorite topics was to have people get charged up and form chains of people charged up. But this is a German scientist, Georg Matthias Bose, who wrote to the Royal Society of London. And in that day, French was one of the two scientific languages, Latin being the other one. And he noticed, he connected an evacuated tube to his machine and noticed that there were interesting sinuous glows in the tube that looked quite a bit like the aurora borealis. So people were making the connection that if you have a very low density gas, like an evacuated tube or like the upper atmosphere, there's probably something electrical going on. In fact, Ben Franklin, who's known for his work on atmospheric electricity, developed very hand-waving arguments about the aurora, and he started from the idea that the upper atmosphere is in fact a good conductor, and proposed that clouds would develop electricity that could flow to high latitudes where the cold air would sink and you would get discharges in the air. It turns out this theory was not really one that survived scrutiny. Another thread of research is geomagnetism. So it had been known that the Earth has a permanent magnetic field, but it was also discovered that there were very small daily variations in this magnetic field. George Graham discovered this. And starting not too long after, some series of regular observations of the Earth's magnetic field and its variations were taken, particularly by Olaf Fjorter in Sweden. And these points are plots of his data. I got this slide from Leif Svelgaard, who's done some historical research and was interested in analyzing these data in particular to see if they could tell us something about variations of the solar cycle, because it has since become known that the amplitude of these variations is related to the sunspot number, to the solar cycle. Fjorder also discovered that the variations became disturbed or stronger when there was aurora overhead. This is just an example of a more modern day magnetogram, a magnetic trace for 3 days, showing the regular daily variations, a station in Peru, and showing what happens when a magnetic storm hits. It's an obvious disturbance that comes about. In the 19th century, there was further advances in the understanding of the electrical properties of the upper atmosphere. Gauss did analyze magnetic data from all over the Earth, and he believed that the primary source of magnetic variations of the magnetic field and variations was inside the Earth, because the data were not sufficient really to determine, although he developed a theory for how one could determine how much of the field is outside and how much is coming from inside the Earth. And in fact, he left open the possibility that some part of the magnetic field is coming from outside the Earth, and based particularly on the observations of the northern lights that seem to have the appearance of electricity and motion. So we get to somewhat more modern ideas with Balfour Stewart, who again considered the upper atmosphere to be electrically conducting, and proposed that if we have winds, this would move the conductor through the Earth's magnetic field, generate electric currents like a generator or dynamo, and those currents could be water affecting the magnetic field. It turns out this theory is correct. So roughly speaking, what we have is on the day side of the Earth and the upper atmosphere, there are current vortices flowing around in the northern and southern hemispheres. And if we imagine this pattern is somewhat basically fixed with respect to the sun, so the Earth is rotating under this pattern, and if we follow a given station underneath this pattern, we'll see, for example, a variation of the declination of the field, first positive, then negative, and the whole variation is going to depend on the latitude of the station. This is a series of stations at various latitudes. And then yet one more thread of research that pointed to the electrical properties of the upper atmosphere was a demonstration that it's possible to propagate radio waves across the Atlantic Ocean around the curving Earth. And it was proposed then by Arthur Kennelly and Oliver Heaviside that this was due to the fact that we have a conducting layer in the upper atmosphere. I think this is a sketch by Leif Svalbard, just indicating how you can get a waveguide between the Earth and the ionosphere. It was found later that the ionosphere has multiple layers in height, and one of the people who developed a theory for the formation of these layers was Sidney Chapman. So our current picture or understanding of the upper atmosphere, first of all, what do we mean by the upper atmosphere? And different people have different definitions of what we mean. Sometimes it's used to include the ozone layer in the stratosphere and as well as the ionosphere. More commonly, when we say upper atmosphere, we're thinking of the part of the atmosphere in the mesosphere and thermosphere that affects radio waves. So the main source of energy for the upper atmosphere is the absorption of ultraviolet radiation, solar radiation, which not only ionizes a very small part of the upper atmosphere, but also heats it up. And so we call this part of the atmosphere the thermosphere because it has a temperature on the order of 1,000 degrees Kelvin. Another source of energy is electric charged particles, that energetic particles coming in from the magnetosphere, and electric currents associated with them that produce additional heating in the upper atmosphere. But we also have significant sources of energy coming from below. In particular, there are waves, atmospheric waves of various scales, small scale to global scale, that propagate up, and as the density of the atmosphere becomes less, their amplitudes grow and can grow to the point of actually breaking and producing turbulence. And also, it's some of these waves that are moving the conductor around and generating electric currents. So Dick Hansen pointed out that Sidney Chapman spent quite a bit of his retirement years at HAO. Some of the other early researchers who came for visits in the 1950s, Sadami Matsushita, who came and became a permanent staff member, Julie London and Bernard Horowitz were visitors and then got faculty positions at the University of Colorado, with which HAO was affiliated at the time. So in fact, I came as a postdoc and worked with Matsushita. This is just an example of some early upper atmosphere modeling work that we did. We produced a simulation of turning on electric currents in the auroral region of the upper atmosphere for about an hour, and then ran the model for a long period of 6 hours, which was a long period in the 1970s to run a model like this. We found that strong winds developed in the auroral region and also started generating waves that would propagate out. This is a snapshot after 3 hours after the simulation. So we've got these waves that show up in the velocity and the temperature. But elsewhere in NCAR, there was research on the upper atmosphere going on. Ray Roble did research on the subaraural red arcs, other aeronomic phenomena. This is an example of some work that he did with Paul Hayes from the University of Michigan, modeling the global electric circuit, atmospheric electric circuit. So connecting the electrification within storm clouds, thunder clouds in the lower atmosphere, and modeling how they connect up with the ionosphere. But a more important type of research, or a bigger effort, that Ray carried out was in conjunction with Bob Dickinson and Cicely Ridley. Bob was in the dynamics, I should mention at this time, Ray was in the atmospheric chemistry and aeronomy division of NCAR. Bob was in the dynamics division, I forget what it was called exactly at that time, and Cicely was in the computing division. They took a model of the lower atmosphere and adapted it to upper atmospheric conditions, to produce the thermosphere general circulation model, a three-dimensional time-dependent model of the upper atmosphere. It was in 1984 that Ray and Barbara Emery and I, this is not me, I don't know who that is, we moved to HAO and joined the HAO team. So we continued developing the model and added an interactive ionosphere, interactive electrodynamics, and this now has become a model widely used in the upper atmosphere community. This is just an example of a 24-hour simulation, if I can get it going. Try it here, okay. This was done by Gang Lu, looking at the disturbance of the upper atmosphere over a 24-hour period during a magnetic storm. And as energy is put into the high latitudes due to the electric currents, we get large-scale wave features propagating out, and also a general increase in the density of the upper atmosphere. This is something of interest for trying to track space objects. Just one more example. This now is looking over a longer period, a one-year period. I think Ben Foster did this simulation. And we're looking once per day, a snapshot as we progress into northern summer and then back into southern summer. And the variations you see are due to variability of the solar radiation coming in, and also magnetic storm conditions putting energy in at high latitudes. So the model is able to generate the types of electric currents that are observed. This is the type of the two-vortex system modeled by the TIGCM, and it's compared here with a model based on observations of the magnetic field. There's other modeling work done in HAO. This is the global scale wave model. This has been used to provide boundary conditions for the TIGCM. Maura Hagen has led that effort. I should also point out that there's an important observational effort related to the upper atmosphere going on in HAO. And this is largely led by Chen Wu, who has set up Fabry-Perot interferometers to measure air glow, the Doppler shift, and width of air glow lines, giving the winds and temperature in the upper atmosphere at various places around the Earth. HAO was involved with the timed mission, and more recently, Chen developed a balloon-borne mission to be able to take daytime measurements of the air glow in the upper atmosphere. Of course, we are also interested in knowing how solar disturbances interact with the Earth's magnetic field to produce the aurora like this. There have been two primary ways that HAO has been analyzing this. One is based primarily on, again, on observations, so observations of these ground magnetic variations at high latitudes, along with radar measurements, satellite measurements, to look at changes in the aurora over time between a quiet time condition and a storm time condition, and also the energy coming in through electrical heating or Joule heating of the upper atmosphere. And to give an idea of how the dynamic nature of the electric fields that are affecting the upper atmosphere, this is work done by a recent postdoc, Ellen Cousins, developing data assimilation techniques to take radar observations from the SuperDARN radars, shown by the colored points, and to combine it with climatological information and information about coherences over different spatial scales to map out the electric potential over the polar region and show how it changes fairly rapidly at 10-minute intervals here. The other direction that we've taken is through modeling the magnetospheric interactions with the upper atmosphere. This is work led by Mike Wiltberger, Wenbin Wang, and a number of other people have been involved in this. They start from a hydrodynamic model of the magnetosphere, use it to predict the types of electric currents that will flow into the upper atmosphere, as well as the energetic particles that produce the aurora. Using that, solve for the electric potential, which feeds back in, as a boundary condition in the magnetospheric model. So then this current state of modeling at HAO for the upper atmosphere, this is the regime encompassed by the coupled magnetosphere-ionosphere-thermosphere model that I just mentioned, starting at about 100 kilometers and going out to include the entire magnetosphere. Other efforts that have gone on, one is that the TI-EGCM I mentioned has been extended by Ray Roble and Cicely Ridley down to about 30 kilometers to look at interactions in the mesosphere and the upper atmosphere. And then more recently, the whole atmosphere community climate model extended into the thermosphere has been a major effort involving almost the entire upper atmosphere section of HAO. Stan Solomon will talk more about this modeling effort tomorrow, and Hanli Liu will discuss the WACM-X effort considerably more. So I'll leave it at that. Thank you for your attention.
Do we have any questions?
And I could just leave some words of advice from an old-time atmospheric electricity researcher to the current generation like myself.
Hello. Oh, there we go. There was one thing that I'm interested in historically is apparently Sidney Chapman was quite vehemently opposed to the some of the views that the Norwegians held from Birkeland, and given that Birkeland is a figure that's on one of the currency notes of Norway, it seems like quite an important figure for them. Do you have any knowledge of what that discussion was about?
No, Birkeland also had the idea, and based again partly on laboratory experiments, that if you have charged particles surrounding a large magnet, some of them will stream in along the magnetic field lines and potentially, in the Earth's case, could produce the aurora. Sidney Chapman, I'm not sure exactly what his objections to that idea were. Other than that, perhaps he was originally a mathematician, so he liked to develop mathematical models, and he had analyzed ground-based magnetic data. And from those ground-based magnetic data, it's possible to produce these images of these vortices of current in the upper atmosphere that are flowing entirely horizontally. You don't need to have any connection from outer space. But I can't say why he would not like the idea of currents flowing along the magnetic field.
It's getting recorded, so that's why you need them.
You're going to lose weight doing that. Recently, I've seen photographs of a new phenomena that I would like you to comment on, and that is something called sprites. In the equatorial regions, you have these huge thunderstorms, but instead of electricity coming down, as one of the slides you showed, there's also this really tremendous flow upwards. And I was wondering, what's the current picture of that? What's the current understanding?
Yeah, the sprites and related phenomena, elves, and I think there's a other types of visible phenomena seen above thunderclouds is still, we have some general ideas of what causes it, but they're really not understood very well. It appears to be that it is basically a type of discharge happening from the tops of thunderclouds upward, up into the mesosphere, well, and ionosphere. Exactly how much energy they carry, it's possible that they carry enough current to be a significant factor in this global electric circuit that Ray and others have modeled. It's not really sufficiently well known quantitatively yet what that is.
I witnessed one of those myself when there was a volcanic eruption at Mauna Loa, and there were thunderclouds in the distance. I saw the condensation from the volcanic gas zip up, and that may be related to atmospheric whistlers.
Then Art, have you ever been lucky enough to see aurora yourself?
Yes, I have, but not a very dramatic display. I visited Kiruna once, and there was a mild aurora off in the north.
Hello. Yeah, you showed some historical documents that people in the 18th century had the hypothesis that the upper atmosphere was conducting, which seems like a pretty bold hypothesis for the time. Do you know what their ideas were, as to what would cause conductivity up there at that time?
I have not found any anything that gave an explanation. It just seemed to be based on these experiments that if you evacuate a tube and connect it with static electricity, it appears that the electricity will flow through the tube. And so people made the connection that simply low density gases could be electrically conducting. I think it was not until either the very late 19th century or early 20th century where the idea of radiation from the sun causing this conductivity came from.
Very interesting. Let's thank our speaker again.